All right, so the kind of big underlying assumption that we had is that we had this little laundry list of things that were all identified to be B-smooth. I've already kind of given you this list of things, and then from that, we're going to try to build these correct little exponent vectors, which are then going to give me information about which of those tools I should actually use as I go forward. So now we're actually going to jump back to the kind of first question, is that we have this relation building stage, which is then going to be connected to this question of how do we actually know that these CIs are going to be B-smooth numbers? We had these 4 over here that were all 7 smooth, and that was great because I could do some very quick arithmetic on those things to actually generate some of these factorizations. But I have to do that a little bit more cleverly. So what ends up happening is that if I start with this number n, if I were to think about running this classic Fermat factorization, what's going to happen is that I'm going to, take the number from 1 up to n and then somehow cut it in half, quote unquote half, at about the square root of n. And that becomes my place that I begin to wiggle to the left and wiggle to the right. What I have here is that my square root of n, floor or ceiling up to the top, is going to be the number 789. So that becomes my first little AI value. So I'm going to take that number, then I'm going to square it, and then reduce that number mod n. So the 789, that becomes my first A. If I square it and reduce mod that number n, it's going to generate the number 590. And then I continue this process by just adding 1 to each of those AIs. So I'm going to have 789, 790, 791, all the way up until I feel like stopping, which in this world meant I stopped at 799 because that's as many as I could fit on this screen. But in general, you're going to spam that thing out really far and then begin to look for some of these B-smooth numbers. What I wanted to do over here is I was looking for things that were 7 smooth. So here's where a little bit of trickery is going to come into play, is that I don't want to go around and actually try to factor each of those numbers because that's a lot of work. Remember that this whole process is all about, this concept that factorization is challenging. I don't want to sit and factor, 10,000 things to just simply factor one thing. So I want to begin to try to do this a bit more elegantly. And what's going to happen is that I'm going to begin bringing about this idea of sieving again. Is that I'm really only looking for things that are going to be made out of 2s and 3s and 5s and 7s, or however high I feel like going. So just go looking to see if objects have that inside of them. And then once you get to a certain stage, stop. And then if you still have other things, then you know that you can throw those objects away. So what I mean by that is I can take this little list of, 12 or so things, and I can begin dividing by objects. What I'm going to start with is I'm going to start with a 2. So I'm going to take all of those numbers. Maybe. Oh, jump back. All right, so I'm going to begin to divide these objects by 2. Sorry for the little kind of jump around in this case. So I'm going to divide all these objects by 2. So what you can see is that every other object is actually going to be even. So I'm going to take the 590 and I'm going to divide it by a 2, which in this world is going to then create simply a 295. Jumping up to, I'm going to take the 3750, divide it by a 2, and so on and so forth. What ends up happening is that if a particular number is actually divisible by 2, every 2 objects from then on is also going to be divisible by 2. So you know what terms are actually going to need this division by 2. So the 2 one's pretty nice because it's every other object. So you're going to take the 590, divide it by 2, and then you keep on going. What ends up happening is that you're going to try to see if after that initial division by 2, any other 2's are still going to be there. In this particular run, every single number only had 1 2 inside of it. The 590, 1 2. The 3750, 1 2. The 6918, only 1 2, and so on and so forth. But when I begin to ratchet up to different types of primes, I might see additional things occur. In particular, if I start dividing all of those things by 3, you're going to see that some of them are going to have more than 1 3. In particular, if you look at the number 8505, if you begin dividing that thing by a 3, you're going to see that a whole bunch of 3's live inside of that. In particular, there's actually going to be 5 3's inside of it, which is, going to take that number 8505 and shrink it down very quickly. Just as with the 2's, once you see something that's actually going to be divisible by 3, every third thing is also going to be divisible by 3. So this first thing was divisible by 3, and then if I go 1, 2, 3, that one's divisible by 3, 1, 2, 3, that one's divisible by 3, 1, 2, 3, that's divisible by 3. But that's not the only collection of things that are divisible by 3. This one, the third entry in that list, was also divisible by 3, and then every third thereafter is going to be divisible by 3 as well. So it's a nice little kind of trick to begin to shorten up the amount of computational effort you actually have to do, is that once you see things divisible by some object, you just can spam it with that collection afterwards. So if I keep this process going, I can divide things by the 5s that they may have. You can see the 295 for sure has a 5 inside of it. It's actually got a whole bunch of 5s. Same thing with the 625. It's got a whole bunch of 5s. It's got 4 of them. The 35's got 1 5 inside of it. The 3895's got some 5s, and the 305. Just like before, once you have some object, every 5 after it is going to have a 5 in it. Same thing here. So you can kind of see that reduction of effort that's going to come into play afterwards. And then if I do my very last stage of dividing by 7, you can see that the 7 is clearly divisible by 7, and the 5047, it's actually got a couple 7s in it, creating that. And this becomes my stopping place, is that I'm going to do this pass of all of these little primes that I'm looking to see. And then once I've gone through all of them, I'm going to kind of look through the rubble that's left over and see if I can actually identify my smooth things. What ends up happening is that if these numbers turn into a 1, I know that the only factors inside of that object are going to be things less than or equal to 7. That is, they're actually going to be 7 smooth, which are actually 2 of the candidates that we saw earlier. The idea is that I had the 3750. We knew that that thing was 7 smooth. In particular, it's actually 5 smooth, and you can see that emerge in this case as well. You took this first pass, you divided by a 2, and then we divided by a 3, and then we divided actually by 4 5s, and we were left with a simple little 1. The 8505 didn't have any 2s inside of it, but it had a tremendous amount of reduction at the stage of 3. So it went from 8505 down to 35, and then the 35 went down to a 7, and then the 7 into a 1. So once you do a bunch of these passes, you're going to see some extra little residues remaining. What I'm hoping to see is a bunch of 1s. Those 1s are actually going to be representations that the number I started with, those things, were in fact 7 smooth. Also, you get some extra information along the way as to how that particular number factored. If you keep track of how many 2s and 3s and 5s and 7s were inside of those things in the division stage, you actually automatically know the overall factorization, which is going to be necessary when we actually build these exponent vectors. Is that once I saw that little matrix to do the linear algebra on, I needed to know the correct little exponents that were in play. So this is where the bulk of the effort in this factorization process is actually going to be living, is that creating this list and doing this process effectively has a potential to, speed things up, or it also could go pretty terribly slow. So that becomes kind of where a lot of efforts are, is kind of running through these lists, constantly doing this test for various smooth things is going to have some computational effort living inside of it.